Welcome back to the second video of quick bug fixing in Radare. Today I'm gonna explain a question that was posted to the discussion channel in GitHub. Basically, the question was about setting environment variables with null bytes, something that's usually needed for exploiting when you have control on the environment variables and there is kind of like an overflow when copying the data that is set in the environment of the process. And after that, you can probably take control on the stack and the execution control flow. So the problem is that in the environment, you cannot set null bytes. So let's check, for example, in the man page for getemp. You will see that getemp in Unix takes const char, which means that it's assuming that it's a null byte string that ends with a null byte, and same goes for setemp. So it's assuming that the key and the value are ending with a null byte. So this is a problem when we are trying to set this kind of data in the in memory. But I had an idea, something funny that maybe it can be used for setting this kind of bytes. So the idea, in short, was basically to set an environment variable replacing the null bytes with a different character. So let's say we have hello world in the hello.txt file. We open the file with the W command line flag, basically because we want to write. And here, pressing C, we enter the cursor mode. So we can replace this 20, which is the space, with a null byte. And now we can just press Q twice, so we can examp the hello.txt file that contains the null byte inside. So what we want to experiment is to modify the environment of the process with the contents of this file. We can use radare2, which is a tool that comes with Radare. And this tool, as you can see, comes with a different profile options that you can specify the program name, the arguments, and the arguments or anything like the environment can be taken from the file. The R strings can be also the output of a command. This is very handy if you are doing exploiting, because you can basically control or set up the environment that you need to run the program. You can also disable the ASLR. You can also set up a different chroot. You can also define that you want to kill the process after a specific time, and you can even replace the standard file descriptors to be using a socket file or a UDP port. Then you can basically use netcat to read the output of the command, stuff like that. So it's very handy. So I recommend you to read the man page of radare2, and you can probably get some ideas about the stuff that you want to do. Another important thing is that when you're debugging with Radare, the process is spawned using the radare APIs, which means that all these options can be used to spawn the program. So you can debug a program inside the chroot just by spawning Radare, and load your custom libraries, change the arguments, and do whatever you like. So let's come back to the thing that we want to load program, and using the hello.txt contents of the file as an environment. So let's do setemp equals foo equals at hello.txt. So what this thing is doing is setting the full environment name with the contents of this file. But we need to specify that we want to do something, but which program we want to run. But for now, we will just not run anything. As you can see, there is an error message here saying that these contents contain null bytes. So radare is smart enough to run a different setemp function inside the R2 APIs that is basically hacking into the stack of the process and modifying the contents to contain that. First, let's see how this is implemented. We can go into the source code and go into liber util sys setemp2. And here you can see that it's basically taking key value, and the value contains length. This is because the length of the environment can contain null bytes. if you want to hack into the key containing null bytes, you can also do the same thing, because at the end the difference is just the position of the equals in memory. You will see that later when we inspect the process memory. So the hack that I implemented here is basically using setemp with the key, but replacing the null byte. So if this is a null byte, it's iterating over all the bytes from the value. And if there is a null byte in there, it's replacing that with the uppercase X. And then it's setting with a standard function call. This works also on Windows. And after that, it's calling getEmp. The thing is that getEmp is returning a pointer to the same process memory in stack that contains this thing. And then it's iterating over all the positions of the zeros that have found, and then replacing that zero, that uppercase X, with a zero. So after that, you get the environment containing null bytes. There are some problems, but first of all, let's run this thing and let's inspect this process. So what we can do here is, because we can attach a debugger, and I will showcase R2Frida to do that, but in order to make things easier, I will just use the getPit profile option that will give you the process ID. We can just run R2Frida : / and then the process ID. This will be attaching to the process and reading the memory from there. Well, now we need to find out where is the location in memory of the foo. So let's run dxc foo getEmp foo. What this command is doing is basically all the R2Frida commands start with colon, which means that this is a command that will be executed through the IO system interface, because Frida is an IO plugin, so if you want to run a Frida command, you need to prefix it with a colon. And then we have the classic radare command style, which is debugging, execute, call. And this is basically resolving this getEmp symbol inside the target process and calling it with the given arguments. We do that, and then we find out this pointer. We can seek there, and now we can just go into visual mode. We can see that there is hello world with a 0 and the null bytes inside, and we can see that there is this foo equals. So let's see what happens if we run the same thing by just using program equals /bin/ shell script, and then we can just find out the process ID, replace that thing, and let's run the same dxc, and we get there. We'll see that this hello is truncated. The reason for that is because when the system spawns a new process, it will be basically replacing, well, it's creating a new environment. This means that it needs to be iterating over all the key values. And if you can see how the key values are defined in memory, are basically key values with the key and then the value after the equals, and there is null bytes after that. So what the process will be doing, what the system runtime linker will be doing, is basically assuming that there is nothing after the null byte that we set there. So the value will be lost. We will be losing the what's after the 0 byte. So how can we solve that? In order to fix that thing, we need to basically use a shellcode encoder. Radar comes with another nice tool that's called radare2, which is a tool for creating X, which is basically something that contains a shellcode. We can check the man page here, but basically what it will be doing is packing the bytes that you are providing. So if you have a shellcode that contains null bytes, you will be providing that with the uppercase B flag. And after that, we will select specific encoder. You can also select the architecture, the bits, etc. Right now, you can list the plugins that are supported here, which is there are like 3 different shellcodes, one for running a standard shell, and then you have bind and reverse shell shellcodes. This is supported for different architectures and operating systems, but what we care now is basically the encoders. There are a couple of them, but it's pretty easy to write plugins to extend that and make radare2 as powerful as Metasploit. So the first one is nullby, and the second one is short. Short is a standard shellcode encoder, but I wrote the null byte just to exemplify how this thing works. What the shellcode encoder is doing is basically taking the shellcode that you wrote and replacing the contents of the shellcode with an encryption that replaces the contents of the shellcode. So at the end, you basically get a prefix shellcode that runs and modifies the shellcode that will be executed after that. And after modifying or decrypting the shellcode, it will be executing it. So let's first try to execute that like this. So we get the shellcode, and let's make like a fake shellcode containing a couple of uppercase A's and null byte in the middle. But this contains no encoder. So let's select the architecture and now use the null byte. So the null byte thing is basically telling you that the null byte is not provided, and it will be using uppercase 41 as a key, which is probably not valid because we are not having, there is the 41 inside the shellcode. So after that, it's identifying that this byte is used inside the shellcode, and it will be using a fallback to the valid one, which is 01. So it's replacing this character with the 01. So let's try to configure null byte plugin by using a different key, like for example 80, and you will see that we'll be replacing that and the warning is gone. Okay, so now we have the shellcode. So how can we disassemble that? We can pipe this to radare2 uppercase -d to read from the standard input the output of that and then disassemble that. But we need to specify the architecture because by default I'm running this thing in an ARM64 box. So we can just see that the output is like that. The problem is that, as you can see, the shellcode is running a call 9, which is running inside the middle of, so it's calling inside the middle of the shellcode. So we need to copy that into Radare and use Radare for analyzing that properly. So we have the shellcode. As an R2 script, we'll load Radare using x86 64 bits. And then we will now write the contents of this file. You can see that the shellcode thing is like this, and we can now just write in hexadecimal that thing. And now if we go into visual mode and press P again, we will see that disassembly. So what we will do is basically pressing L to move one byte to the right, another byte to the right, another byte to the right, and at the end we'll be jumping to the position 9. We can just also seek 9 in order to find out which is the destination of the call. And then we get that the whole disassembly makes sense now. So to make it easier for the reader, I will just go and read the source code of the shellcode that I wrote. So you basically have an entry point that it's setting BL to value 0. So this is the same as BL equals 0. Then it's using RCX 0, and then it's calling me -1. The reason for that is because if you run call me in order to find out the program counter in the next address, because we need to know where the shellcode is located in memory in order to patch the shellcode itself. We need to basically, this call will be containing null bytes, and this is not what we like. So what will be here is calling the next address -1, which is also a valid call, and this is basically 9 plus 1 is A, and what it will be doing is basically calling to this address that is also a valid instruction, but it's basically incrementing ECX ones, which is something that we don't really care. So after that we pop the value from the program counter in this pop RDI, and then we add the address in RDI and also the RSI. We'll use these RDI and RCI registers as source and destination for iterating over the shellcode and patching that. So for example, as you can see, there is a loop, and this loop is iterating CL things, and this PSX is the program of the payload, which is the size of the shellcode that we are gonna patch. And then after the alteration is done, it will be replacing all the bytes that contain the key that we used as a key, which is this uppercase A by default, with the null byte, which is the value of BL. As you can see in here, it will be modifying this byte. And after that, we can see that the shellcode, the real shellcode, is here, right after the loop. Okay, so we have all the shellcode written here. Let's analyze the same thing in here. You can see that there is like the loop that's calling there, and then the writes from that. And that's it. So you can see that now the final shellcode doesn't contain any null byte. It's containing the byte that we like, and we can use this shellcode for exploiting the environment properly. So we can just copy paste that into a file and use that with radare2 to set up the environment with a right value, and the child process that will be executing with the environment will contain the shellcode ready for your exploit. And that's it. I hope that you learned some stuff. I will probably show you, if you're curious about the egg plugins, you can read that stuff in the libair-egg, and you can find the source code of the null byte plugin in here. So probably the interesting part is that the default key is 41 that you saw before, and there is only one function that is called build, and this function is using the key configuration option to change that default key. And after that, we have the shellcode. We can just scroll down, we have the full shellcode in here, and at the end, we can see that it's replacing the payload size and the character that will be used for setting the null bytes after that by patching the shellcode itself. So at the end, we get a new buffer that contains the patched shellcode prefixed with the shellcode encoder, and it will be returning that buffer. So that's it. So now you can write your own egg plugins for encrypting shellcodes or patching stuff, or creating your own shellcodes in here. And you can also use radare2 for creating the right payloads for prefixing with knobs or traps interactions if you already need them. So that's it. Hope that you learned some stuff and you can experiment with some tooling in Radare for exploiting. Don't forget to like and subscribe. See you in the next video.